Good morning. Good morning. Can you all hear me okay?
Yeah.
Okay. All right. So why don't we get started? Let me just adjust something on the camera. Okay. Is the writing on the board a little bit blurry?
I think it's fine.
It's fine. Okay. I'm going to shut off my autofocus. All right. So just some announcements. I'll be lecturing from campus on Friday. So if you have questions on Friday, then you can come ask, you can come talk to me. Okay. Don't forget, Ohm's Law is due on the 29th. The exam is also on the 29th. We'll be in person, and from then on, like, as a reminder, all the labs will be in person. Okay. The DC Circuit Lab, which I'll present on Friday, is due on November 5th. And then I'll also introduce the Motor Lab. It's more like a project. You'll have several weeks to build a motor and demonstrate that it works. And then the Chapter 28 homework is due on the 26th. And by the time I'm done today, you'll have enough information to pretty much do most of the homework in Chapter 28, okay? So what I want to do is I want to start with another example of DC circuits, and this is going to lead to solving more complicated problems. So I guess let's review some things regarding what we've learned about DC circuits. If you have resistors in series, they add. If you have resistors in parallel, they add as reciprocal. So I'm going to write it in a compact form. So it takes up less space on my board. Oops. So this whole thing is to the -1 power. Okay, and of course we have delta V is I times R. And of course, the way this is written here is delta V is written as a positive number. Okay, right now this is written as the magnitude of the potential drop. We also talked about the fact that the sum of the voltage drops across any loops is 0. And the sum of the currents entering or leaving a node is equal to 0. I'll use a capital I. So this is the Kirchhoffs voltage rule. This is Kirchhoffs current rule. And so in this problem, I'm gonna do this a couple of ways. Let me draw the circuit. I have two resistors, 2.5 kilo ohms, power supply, and then I have another resistor here, and another power supply. This one's hooked up the other direction. We're ignoring the internal resistance of the power supplies or the batteries. So what would you do in this situation? Anybody would want to say what you would do?
Is there a way to hook up the batteries in some sort of way? Maybe.
Hooking them up like this?
Yeah, like maybe hook up the batteries and
I'm sorry, I hear a lot
parallel
of,
maybe.
I'm hearing a lot of background noise. Go say it one more time. I'm sorry.
Sorry about that. I have someone else now. Is there a way we could manipulate like the things with like the batteries? Maybe. Okay. Yeah. Just.
Well, we can combine these two. I mean, you did this. You did this in the lab. The multimeter quiz. You connected two batteries in series, right?
Yeah.
And so that's basically what that is two batteries in series. And if you notice, the potential increases 1.5 volts here, and then as you go around, the potential increases another 9 volts. So really, this is the same as a 10.5 volt battery, isn't it?
Oh, okay, gotcha.
Because basically what you have is something like this. That's the same thing, right? So that's 10.5 volts. So I can replace those two with the 10.5 volt battery. Okay, so I'm going to redraw it. And what about the two resistors? How are they connected?
Those are also in series, right?
Yeah, so this is really the same thing as a 7.5 kilo ohm resistor. And so my current then, using this equation, I, is going to be my voltage, my potential drop, over the 7.5 kilo ohms. And I'll get something in milliamps. Okay. And again, when I'm doing this, I'm solving for the magnitude of I, right? Because I made this a positive number. So we're okay with that? So we use some physical intuition in Ohm's law to figure this out. But I want to show you another way. I want to use this idea that the sum of the voltage drops in any loop is zero. It's gonna be more work for this particular problem. But when we do more complicated systems, it's going to be very useful for us. Okay, so I'm going to do it the other way. And I'm going to say, I'm going to actually pick a direction for the current. I'm going to say, well, my current goes this way. Okay, and it pretty much makes sense that the current's going to go this way. We okay with that? Then I'm going to go around and sum the delta V's. I can go either clockwise or counterclockwise. That's your choice, or my choice. I'm going to choose to sum the voltage drops clockwise. I'm actually going to sum in the direction of the current. So what am I doing there? Remember that the current, what I got before was 10.5 over 7.5, okay? So what am I doing here? Well, delta V is minus the integral of E dot dr. So the current is proportional to the electric field. And the current is in the same direction as the electric field. So when I'm counting voltage drops, summing voltage drops in the direction of the current, I'm actually integrating in the direction of the electric field. This dot product will be positive. And of course, there's a minus sign out here. And so my delta V will be negative, indicating a voltage drop. So I'm going to consider this voltage drop as a negative number. And I'm going to say, okay, well, if I start from this point and I go clockwise, I'm going to start with minus the current times 2.5 kiloohms. I hit this battery goes from a lower potential to a higher potential. So its voltage, its potential increases by 1.5 volts. Then I hit this one. And then I continue, my current is in this direction here. I continue to sum in the clockwise direction, in the same direction as the current, the same direction as the electric field. And so that's the voltage drop according to my convention. And I'm running out of space. This is equal to 0. So I can collect terms. 2.5 and 5 is 7.5. And these two add up to 10.5. Solve for I. And I get the same result. And I use the idea that the sum of the voltage drops in any loop is 0. Right, and then that makes sense. I mean, if I have, just to simplify it, I have a bulb and a 3-volt battery or 3-volt power supply. This points at 3 volts, this points at 0 volts. So the voltage goes down here. Oops, I had that backwards. Okay, the voltage goes down by 3 and then it goes up by 3. You have a drop of 3 and a gain of 3. The sum of those two is 0. Negative 3 plus 3 is 0. That's the current, that's the voltage rule. And so when you integrate this around the loop, I get 0. Does that make sense?
Could I ask how you found out that the current is going that specific direction? Why couldn't it go the other direction?
It could. I chose the direction. So suppose I chose my current to be in the other direction. Okay, and I still summed clockwise. What would that mean? Well, that would mean then this dot product is negative, right? Because I have two I'm taking the dot product of two vectors in the opposite direction. So this dot product will be negative. A negative times a negative is a positive. And so these would all be voltage gains. And then when I solve this, I got a minus sign. What does that minus sign tell me?
You're going opposite to the electric field.
Yes. It basically is saying I chose the direction incorrectly. That's all it does. So I could have chosen either direction and I still get the answer.
Okay.
Okay, that's a good question. Because that's a question that comes up when I do the more complicated problems. And I thought it's good that we see it here, that you brought it up here, because then we don't have to worry about it in the more complicated problems. It's kind of like when you do the torque problems in 205, and you have to guess the direction for one of the forces, because you don't know. And you solve the problem if you get a negative number, that means you just chose the direction wrong. It's the same idea.
So in a problem, do we just flip it if we have a negative number?
Yeah, at the end you just say I chose the direction of the current in the wrong direction.
Okay.
So if you get a minus sign, if you say the current's going to the left and you get a minus sign, then you say, oh, the current's to the right. That's all. You say the minus sign means the current's going to the right. And you're fine. I mean, you don't know sometimes. And you can't help that. This one you kind of know, because here's a negative terminal, here's a positive terminal of the battery. And you kind of know the current's going to go that way. Are we okay with this? Okay.
Could you explain the bulb, the 3 volts and the 0 volts, that again, please?
So let's go clockwise, right? You go from 3 to 0. 0, so the final minus initial is -3, right?
Yeah.
Okay. Then you go from 0 to 3. 3, so the final is 3, the initial is 0. 3 minus 0 is?
3,
Okay, so I sum the voltage drops, what do I get?
0.
Okay, that's all I was saying.
But why did you put 0 on that specific corner? Couldn't you put it like in the bottom right corner and say that's 0?
You mean here?
Yeah.
They're the same, right? They're just a wire.
Oh, okay.
It doesn't matter. I could put a 3 here. I should put a 3 here too, I guess. Because it's a wire, right? It's implied that the potential here and the potential here are the same. I'm just trying to indicate that this is a 3 volt drop and going this way is a 3 volt gain. If I go clockwise.
And it's a drop because of that bulb right there, right?
It's a drop because you go from a higher potential to a lower potential.
Okay.
Okay? Because the way that you have the battery hooked up. The electric field is this way. The electric field goes from the positive to the negative terminal. So this brings in everything regarding the previous unit, right? The electric field lines go from positive to negative. Okay. So now, what if we wanted to do a circuit like this? This is almost like your lab that you're doing, the problem I did the other day, except that the thing in the middle, the resistance, that item in the middle has a non-zero resistance. How do you solve that problem? You cannot use series parallel rules because those resistors are not connected in series and they're not connected in parallel. What do? Well, you actually have to end up using Kirchhoffs laws. You have to actually use these 2 rules. Okay? And I'm sorry if I use the word rule and law interchangeably. Okay, so you have to use these 2 items to solve that particular problem. And you're able to do it. You're able to find a current through each one of those resistors by applying just these 2 principles. Okay. And so what I'm going to do now is talk a little bit about how you can apply Kirchhoff's laws to solve these kind of problems. I'll do an easier example, then I'll do a harder example. I'll do this particular one. And then I have a third example. I'm just going to tell you about it, but the solution is in the notes. Okay. So how do we solve this problem using Kirchhoff's laws? And now I ought to tell you, I actually got the method, because I think this is the best method, from a textbook called University Physics. Of course, this is my opinion, by Young and Friedman. And we do have copies of that book on campus. Okay, so I'm going to use their method to solve these problems. The methods vary a little bit, but I'm going to use their method and their convention. Okay, so we're going to use Kirchhoff's laws to solve these problems. Use the fact that the sum of the voltage drops around a loop is 0. And the amount of currents entering a junction, the amount of current entering a junction has to be equal to the amount leaving a junction. And you don't have to write it as the sum of the currents equals 0. There's different ways to write it. So here's the methodology. The first thing you want to do in solving these problems, and it always drives me crazy when a student draws a tiny picture. You want to draw a nice big picture. Okay, a nice schematic diagram. So you draw a nice schematic diagram of your circuit. And then right away, you apply the current rule, or the current law, however you want to call it, okay? You want to apply it right away. And this will allow you to figure out how many independent currents there are and how many loops that you need to solve the circuit. Okay? Because these are problems where you're going to be using 3 equations, 3 unknowns, 4 equations, 4 unknowns. When you take engineering 17, you'll do problems where you have to do 6 equations, 6 unknowns. Except in engineering 17, you're going to be allowed to use a calculator to solve them. So once you've applied the current rule, then all you need to do then is choose a loop, pick a direction to sum the delta V's like I did in this particular problem, and derive an equation for that loop. Then you pick another loop and repeat it. And you choose as many loops as you have independent currents. And I'll show you what I mean by that in a little bit. Okay. Once you have enough equations, and you got to make sure that the equations are independent of each other. And you learned that in Math 33, right, about how equations are systems of equations are independent of each other. And then you solve them and see if they make sense. And generally you're solving for the current. And if you have a minus sign in your current, that means you just chose the direction of the current wrong. That's all. Now I have some other. I'm not going to show all the notes, all the PowerPoint notes in my presentation today, but some of them are hidden so that you can read through them. Okay, so yeah, there's some extra hints in there to help you solve problems. So what I want to do is I want to set up this problem, and I want to solve it using Kirchhoffs laws. There's actually other ways to solve this problem, and you'll learn them in Engineering 17. But every problem we're going to be doing here is, I would call a brute force method. Okay, just applying Kirchhoffs rules or laws directly. Okay. You'll learn in Engineering 17 techniques that will simplify the problem-solving process. I'm not going to do those here. All right, so let me draw my circuit. This is something you would see in your car. So this is your car battery. This is the voltage across your alternator. Okay. This is the resistance of the alternator. Resistance of the battery. And then this will be your 1.2 ohms. This could be your headlights. I should have drawn it bigger, but I don't have enough space here to write everything down. Okay, and so let me label the points. I'm going to pick a bad color, but because I'm going to need all the colors I can use. So you should realize that the potential difference between these 2 points is the same as the potential difference between these 2 points is the same as the potential difference between these 2 points. Okay? All right, so how many loops do you see there? How many loops do you see?
2.
Do you see a third one? All right, there's 1, there's 2, and then there's the big one out here. All right, there's 3 loops. So I can apply Kirchhoffs voltage law to any one of those loops. But before I do that, I want to designate my currents. I'm going to apply Kirchhoffs current law right away. I'm going to start here. I'm going to say the current here is I. It splits up into 2 parts over here and over here. And I want to be consistent with my labeling in the PowerPoint notes. Okay, so I'm going to call this one I1, this one I2, but I don't want to call this I because I know what this is. This is I1 plus I2, all right? Because here's I1, here's I2, this is the sum of those two, that's it. So really, I only have 2 currents that are independent of each other. This I is dependent on the sum of those 2. Does that make sense? So I only have 2 independent currents. That means I'm only going to need 2 loops to sum over. Meaning I'm going to have 2 equations with 2 unknowns. My 2 independent currents are my 2 unknowns. That means I need 2 equations, so that means I need 2 loops. And I can choose whatever 2 or 3 loops I want. As long as the equations are independent of each other. Questions on that? Okay. So is everyone clear how I chose them? I arbitrarily chose these. You could have chosen a different way. I could have had these arrows pointing the other direction. I could have called this I1 plus I2. I could have called this I1 and that I2. It doesn't matter. It really doesn't matter. Okay? It's completely arbitrary how I designate my currents. And students have a hard time with that. It's like, how do you know that's I1? Well, I just chose that. You choose it however you want. Are we clear on that? You guys okay?
Yes.
Okay. All right. So let me show you in the slide. Those are my currents. The next thing then, once I've done this, and I really should have made this picture bigger, but my board is not big enough. I should have probably drawn it over there. It's my mistake. I'm gonna pick my 2 loops, and I'm gonna pick the 2 small loops. And just for fun, I'm gonna just sum the voltage drops in the clockwise direction. So it's going to go around and sum the voltage drops in the clockwise direction. Okay, and I'll write my equations up here. So let's start with the bottom loop, and let's sum voltage drops. And so what I'm going to do, I'm going to start here and go clockwise. So I go from a lower to higher voltage, that's a voltage gain. Then my current, let me draw my current here. The current through this resistor goes that way, and I'm summing in that direction. So this is going to be a voltage drop because I'm summing in the same direction as the current. And so this is going to be minus 0.1. And I'm not going to put the units, I shouldn't put the units in, because I'm not going to have enough space on my board. Then I reach this resistor. Again, I'm going clockwise. I'm summing in the direction of the current. This is 0.01 ohms with I2 going through it. And then I have the 12 volt battery. Or I go from a higher to lower voltage as the voltage drop. And then I'm done. So that's my first loop. My second loop, I'll start here. Okay, I'll start here and I'll go clockwise. So I go from here to here. I go from a lower to a higher voltage, that's 12 volts. But here's the problem. I'm summing against the direction of the current. If this is negative, negative times a negative gives me a positive. This gives me a positive number. And then I go through and I keep going clockwise and I reach this guy. I'm summing in the same direction as the current. So I have my two equations and two unknowns. Let me rewrite the top one. 14 minus 12 is 2. And then let me simplify this. Okay? So those are my equations. Now I just got to solve them. I am not going to solve by substitution. I actually like doing the following. So what I'm going to do here, I'm going to eliminate I2. And so I'm going to multiply through, by 11. And so as I do that, (11 times 12 is 132). 11 times 1.2 is 13, I think 13.2. Then I'm going to add the equations. These will cancel out. I get 134. Oh, I made a minus sign error. I forgot the minus sign. Sorry.
I was about to ask about that.
What is it?
I was about to ask that.
Oh,
I was wondering where you got the plus sign.
And so I1 is 134 volts over 13.3 ohms. And that's going to come out to be 10.1 amps. So this is 10.1 amps. Of course, then I can go in and substitute into either one of these two equations to get I2, right? And I2, I think I wrote down the wrong value yesterday. I2 is 9.0 amps. And so this is 9 amps, this is 10.1 amps, this is 19.1 amps. That's it. That's all. I'm done. Questions on this one?
How did you know that A to B is current equals current sub 1 plus current sub 2?
How is it that way?
Yeah.
Well, I'm calling this I1, right?
Yeah.
And I'm calling this I2. I1 is going this way, I2 is going this way. And so imagine water flowing through a pipe. If I have some water going this way and some water going that way, where does it come from?
From the bottom.
From the bottom. And so this is the source then, and so this is going to be the sum of these two.
Okay, that makes sense. Thank you.
Okay. The same idea with electrons, right? I'm using the water model, but I mean the same idea. Other questions? Okay, so now we're going to do a harder one. We're going to do this one. So basically it's the problem we did the other day, except we put a resistor across that bridge. The other day that resistance was 0. Here it's not. Okay, so I'm going to draw the circuit over there. And I'll put the values in. So R sub A is 1 ohm. I'm not being careful with sig figs. R sub B is 1 ohm. R sub C is, something's blocking my slide, is 1 ohm. R sub D is 2 ohms. And this one is 1 ohm. Okay? This one's more complicated because I have more loops in it. I have a lot of loops in this one. I have like 5 loops, if I counted properly. So I drew my picture. The next thing I'm going to do is I'm going to designate my currents. And so the easiest thing to do is say, okay, let's look at the current from the power supply. It goes through here and then splits this way and this way. I'm going to call this I1 and this I2. Well, then this must be I1 plus I2. So far, I only have 2 independent currents. But what happens when we get here? Well, some current goes this way, and some current goes that way. So it splits. We'll call it I3, and this we'll call I1 minus I3. Well, if this is I3 and this is I2, they come to this point. This has got to be I2 plus I3. So really, I only have 3 independent currents. It takes a little while to get used to identifying the currents. This is the hardest part, to me, this is the hardest part of the problem. Once you've identified the currents, most of the physics, most of the hard part is done. The rest of it is watching your minus signs and plus signs. when you're adding the voltage drops. Because it's easy to make minus sign. You saw I made a mistake earlier.
Is there a way you could explain why it's I1 minus I3? I just can't seem to wrap my head around why.
It's too small. You can't see it?
Oh, no. I was just asking if you could explain to me how you would get that.
Oh.
I don't know if I just can't wrap my head around it.
So I have current I1 here. And it's split into two parts, right?
Yeah.
One of them we'll call I3. And then the other one, just what's remaining, correct?
Yeah, okay.
I think of it that way. So something that goes, this will be the independent one, and the other one is the remaining, which is going to be the difference between I1 and I3. I'm sorry, it's just hard to hear you. Okay. So I'm going to choose 3 loops. There's a bunch of loops to choose. I'm going to choose 3 of them. And I'll show you in the PowerPoint what they are, and then I'll write them down. So these are my current designations. As you see, the orange colored arrows pop up. Now the green ones are going to pop up. And so my first loop, I'm just going to change things up on you because it really doesn't matter, will be this one. This is loop 1. And I'm going to sum counterclockwise. So that's loop 1. Okay. My second loop, I'll do clockwise. Loop 2, my second loop is this one. Okay. Consisting of the power supply, this resistor, and that resistor. R sub A and R sub C. And then my third loop will be the other one. So here you could make a bad mistake in choosing loops, okay? Suppose I chose this loop, and the diamond. What's the problem with that?
You don't use the battery.
Yeah, I didn't choose the battery. In fact, you'll find if you do that, that the diamond is the sum of these two. When you add the equations for this loop and this loop, you'll get the diamond. So then you would get, the equations won't be independent of each other. You got to make sure the equations are independent of each other. Okay. So, let's look at the first loop. I'm going to use my blue because my blue looks the best. Yeah, the blue comes out clear, I think. So I'm going to choose that first loop. I'm going to go counterclockwise just to be different. Because it doesn't matter whether you go clockwise or counterclockwise, and I want to make sure I start from the same point as compared to my notes. So I'm going to start here and go counterclockwise. So if I go down this way, this is 1 ohm, I have I1, I'm summing in the direction of the current. I have minus I1 times 1, okay? Then I get to this resistor. I'm summing in the direction of the current. That's going to be a negative value. I3 times 1 gives me that. I get to this point, come up here. Now I'm going against the direction of the current. If I'm going against the direction of the current, I'm going to make that a positive, a voltage gain. Since I have 3 independent currents, I have to have 3 loops. Okay. So that's my first one. My second loop is that one. So here's my second loop, this guy right here. I'll start at the battery. I'm going to go clockwise. The battery's 13 volts. I have a voltage gain. Right? I go this way from low to high. Nothing here until I get to this resistor. I'm summing in the direction of the current. And so it's I1 times 1. And then I keep going. I hit this resistor. I'm summing in the direction of the current. So the current is I1 minus I3, and the resistance is 1. And that gives me 0. You just do it slowly. Take your time. Just be very systematic about it, and you'll get to the right answer. Okay. Then the third one is this guy. So again, I'm going to start the battery. I'm going to go clockwise, so I have a voltage gain. And then I hit this resistor. The first resistor is this guy, and I'm going in the direction of the current. And then I hit this resistor. And again, I'm going in the direction of the current. The resistor is 2 ohms here. So those are my equations. Okay.
Professor, why didn't you write I1 plus I2 for the second loop or the third loop?
There's no resistor.
Okay.
Right? There's no resistor here. So if there were a resistor, then I would have to have a term with the resistance times I1 plus I2. But there's no resistor. I mean, the wires, we're assuming that the resistance of the wires is negligible, right? Okay. So those are my 3 equations. So I want to rewrite these. In the following way. I'm going to put them in an order. The second equation, so let me rewrite the second one. This is going to be a minus 2I1, right? Minus 2I1. There's nothing here. There's an I3 here. And I'm going to put the 13 on the other side. Is that okay? And then the third equation, I'm going to put the 13 on the other side. And let's see, there's no I1 term, but there's 3 minus 3I2. And then minus. So I have 3 equations and 3 unknowns. And again, I'm not going to really do substitution. What I'm going to do first is I'm going to eliminate some variables. I'm just multiplying equations by constants, etc. So I'm going to take this equation, and I'm going to take this equation. And hold on a second, I'm going to check my. I'm going to combine them. Okay. So let's take a look at these two equations. I'm going to take the top one and multiply it by 2. I'm going to write over here. Is it okay if I erase this?
Yeah, go ahead.
I don't want to write down there. It's going to take a while. So let me multiply the top equation through by 2. And then the second equation, I'll write below it. So I multiplied this row of equations by 2, and then I'm going to then add these two. So what is that going to give me? Oops, that's not right. That's not right. Look okay? I'm going to subtract them, sorry. I subtracted them, I didn't add them. Okay, so now subtract. Now I'm going to take this equation and put it underneath. And what I'm going to do is I'm going to multiply this by 3 and this by 2. So I'm going to multiply this row of equations by 3 and this row of equations by 2. And what do I get? And then I'm going to add the equations. I'm going to add the equations here. Basically, I'm adding the coefficients, right? I got I3 is minus 1 amp. What does that tell me?
You chose the wrong direction.
Yeah, it just says I chose the wrong direction. That's it. Okay, so the current is to the left. Because I chose it to the right. Then I go back and take this, and I'm not going to go through the work, and put it in here and solve for I2. And you'll find that I2 is 5 amps. Okay, so again, I3 is the 1 amp and I2 is 5 amps. And once you got that, then you can go back to your equations or your drawing and figure everything else out. Does that make sense?
Yeah.
I mean, the The one through RD is very easy because once you have I3 and I2, you know that's going to be 4 amps. And so that picture shows you all the currents. And then you can find all the voltage drops across each resistor. And if you want to find the power dissipated, you can too. Notice I1 is 6 amps. Now, is there another way to solve these equations? Notice how I wrote these. Notice how I wrote this, and I use the term rows and columns. Has anybody had Math 33?
Yeah.
And what would you have done if you were using Math 33?
I forget what it's called, but that.
What is it?
I forget what it's called, but isn't it using...
You set up a matrix, right? Basically, all I did was I multiplied this row of equations by 2. I did that here. And then added it to this row of equations, basically, which is just the coefficients. And I reduced it. And every time I do that, I redraw my matrix. And it's called row reduction. So I'm not going to go through that here, but if you've done row reduction, you can use row reduction if you want. However, when you take Engineering 17, he's going to let you just put all the equations in on your calculator, and then it'll give you an answer. Okay? But in your notes, I actually go through and show the row reduction method for this particular problem. And if you're interested, take a look at it. If not, that's fine. You might have seen this already. There's other ways of solving 3 equations, 3 unknowns. But generally, on my exams, if you're doing if I'm having you set up 3 equations, 3 unknowns, I'm just going to have you set it up. I'm more interested in you being able to set it up. Okay. If it's a 2 by 2, then I expect you to solve that. Okay, because that one's 2 by 2s are easy to solve. Okay. Anything 3 or 3 and above, I'm just going to say, okay, set up the equations, and I'm just going to grade the equations you have. That's it. Okay, because I want to make sure you know how to set things up. Again, I'm interested really in the process. Okay, because going through the math and solving it, it's just going to take time. Are we okay? Any questions?
I think it'll just be getting used to knowing what the directions are. I think that'll be my hardest part, probably.
Oh, it is. I mean, you're right. I mean, you mean assigning the direction of currents?
Yeah.
That's going to be the hardest part. But you pick a place. You start from an easy point and then move on from there. But once you've done a few, it gets a little bit easier. It's hard at first. The way I was taught it was very confusing because we weren't taught to apply, at least I wasn't taught to apply the current rule right away. And so you end up having really 4 equations, 4 unknowns. I would have a 4th equation, right? So it would actually a little bit harder. Whereas here, you apply it right away. Maybe it's not 4 equations. It was much more challenging to do it the other way, as opposed to doing it this way. Designate the currents right away, then you know, okay, I just need 3 equations. Okay. But yeah, it takes a little bit of time, and once you've done a few problems, you'll get the hang of it, and then you'll do it again in Engineering 17. So I set up this problem a different way, just showing you it doesn't matter how you designate the currents. So this problem is solved in your notes. And so I'm still writing all the currents in this figure. In fact, let me make this picture larger. I wrote all the currents as I1, I2, I3. The current through RC is I4, because there's 5 currents there, right? I mean, we know there's 5 currents. And what I decided to do is say, let's make the bottom 3 currents that you see in that picture the independent ones. Let's say we make the bottom 3 currents the independent ones. meaning that the current through the battery is I4 plus I5, which we got to be 11 volts before. And I1 is just I3 plus I4. And then I2 is I5 minus I3. So I want to write all the currents in terms of I3, I4, and I5, and then apply the current rule. And my equations just have an I3, I4, and I5 in it. And I solve them. And if you do, you're going to get the same results as you had before. You can choose the same loops if you want. You can choose different loops, however you want to do it. But in the end, you got to get the same results. But I actually went through this and actually set this up. And I'll let you study it. I don't want to spend time going through this.
So we're allowed to choose our dependent and independent variables.
Oh, absolutely.
Okay.
You're completely free to choose it. You just got to apply the rules properly. That's the main thing, is you have to apply the rules properly. That's the most important thing you have to do, is just do things correctly. And if you apply the rules properly, you'll be fine. It doesn't matter. Now, I want you to be careful, because I've seen this on exams. People will learn the fancy techniques, where the fancy technique is not always the best technique to use. I've seen students do series parallel circuits with Kirchhoffs laws, and it takes them forever to solve them. Okay, don't do that. If you can recognize if resistors are in series or parallel, just use those ideas. Because what we're doing here, this is kind of a brute force method. Even that simple one with the 2 batteries I did at the beginning of class, really that took longer doing a direct application of Kirchhoffs laws instead of knowing, oh, these are in series. Just applying the ideas of series and parallel, that would have gotten you to the answer faster. So just be careful, because I've seen on exams students with series parallel circuits just applying Kirchhoffs laws blindly, and they spend 45 minutes on a problem. Okay, so part of the exam is understanding what technique you need to use. Obviously, for that diamond-shaped one with the resistor going across, you got to use Kirchhoffs laws. And you'll notice in some of the homework problems, I have bizarre-looking circuits, so that to train you to recognize how things are connected in a circuit. Okay, you'll see some really bizarre-looking ones, and they're designed to train you to recognize whether they're series or parallel or something else. Okay. So the last topic in this chapter now has to do with a resistor and a capacitor in a circuit. These are called RC circuits. They're important in timing, for example, like your intermittent wipers. Okay. Of course, the ones in your intermittent wipers are a little bit more sophisticated than just a simple RC circuit, but the basic principle is there. So let me draw the simple RC circuit. We have a and by the way, the order of these doesn't matter in my circuit. And Monday, either Monday or actually, I might even do it on Friday. I'll demonstrate the RC circuit for you. I have a nice big one set up on campus. So this is my RC circuit, and question is, oh, I forgot my switch. I have my switch there. So initially, the capacitor is not charged. The switch is open. Nothing's happening. It's a boring circuit. I close the switch, and then charge builds up on the capacitor. But the problem is I have a resistor here. The resistor is going to oppose the flow of charge. And so this thing is not going to charge up as fast as you would expect. This is going to make it charge up more slowly. We would like to know, what is the current in the circuit? What is the charge on the capacitor at any instant in time? What is the voltage on any one of these elements at any instant in time? That's what we would like to know. Well, I can't use the rules for series or parallel because I have rules for series for capacitors. I have rules for series for resistors, but I don't have any rules for these two things that behave differently. So what do? Well, I have the voltage law. And so I will apply the voltage law. Okay? I will apply the voltage law to solve this problem. It is really not that hard. It is a calculus problem. I don't expect you, I mean, the derivation is not hard. On the test, I don't expect you to do the derivation. I expect you to understand the final results. Okay, but I want to go through the derivation because it's a nice application of calculus. So I'm going to assume the current's this way, and I'm going to sum the voltages clockwise. So I'll start here. I go from a lower voltage to a higher voltage. Let me make it bigger. And then for the capacitor, Q is C delta V. So delta V sub C is Q over C. That's a voltage drop. And then for the resistor, I have a voltage drop. Okay, now what? I know the power supply voltage is a number. I don't know Q and I don't know I. But I do know that the rate at which this charges is equal to the current in my circuit. And so I is dQ over dt. So now everything in terms of Q's. Q's is what I want to solve for. Q depends on time. R is a number. V sub S is a number, and C is a number, right? R and C are just quantities that depend on geometry. Let me put this term on the other side of the equation. And let me multiply both sides by C. Because then this has units of charge, right? Now what? Well, what I learned in calculus is that I got to get all the Q's on one side of the equation, because I know Q depends on time, and I got to get the dt on the other side of the equation. So I'm going to multiply both sides by dt and divide by RC. And I'm also going to divide both sides by this term. So I get the following. And I do this a little bit differently than I'm going to do it here a little bit differently than in the notes. At least you get to see how this is done two different ways. In the notes, I actually put limits on my integration. I'm not going to do that here. So what do I do now? I just integrate, right? When I integrate this, I get minus the natural log plus some kind of constant. Let me call the constant k. So I integrated both sides, and I get this. And then this is my constant of integration. Let me move the minus sign to the other side. Okay? So I multiply both sides by -1. I didn't want to rewrite everything. Let's exponentiate everything. Let's raise everything. So let's exponentiate both sides. So I get and by the way, this is the same thing as this thing. Right. This is a constant. I don't want to write the constant this way. What should I call that? What do you want me to call it? What letter?
Z.
You want me to call it Z? Okay. So
Why
let me.
not?
And I'll figure what this out. This is based on the initial conditions. Okay, so I know at t equals 0, what's Q? How much charge did I have on a capacitor when I started?
It was 0 charge.
0.
0. So let's plug in t equals 0. We know Q is 0, right? So C, or Z, is equal to C delta V sub S. Okay, so I'm going to go over there. So my equation for Q then looks like this. Let me solve for Q. Now, what's C delta V times S? What is that? What's C delta V sub S? What does that represent? What does that represent? Let's think about it. I'll draw the circuit again. The capacitor charges up, right? What happens when the capacitor is fully charged? What's the voltage drop across it? Well, first of all, how much current is going through the circuit when the capacitor is fully charged? What does it mean when the capacitor is fully charged? We have to know what these mean. What does it mean? Anybody? What can you say about the current when the capacitor is fully charged? Are there electrons moving when the capacitor is fully charged? We learned that in chapter 26.
No.
No, there's no current. So if there's no current, that means that the voltage drop across the resistor is 0. The voltage drop across the capacitor is the battery voltage. The voltage across the capacitor is maximized when it's fully charged. That means it has the maximum amount of charge. And so I'm going to call this Q max. So C delta V sub S is the maximum charge that you can place on the capacitor in this circuit. And so this represents the charge on the capacitor as a function of time. Now, what are the units of R times C? What do you think? Anytime you have a function in something in an exponent, what must be the dimensions of the exponent? What are the units in the exponent?
Some time.
The exponent can't have any dimensions. I mean, when you do e to the x, this thing has no dimensions. Cannot have any dimensions. Were you guys aware of that? I guess not. Okay, so this ratio has to have no dimensions. So that means R times C has to have units of time. So why can't e to the x why can't the x have dimensions? Well, isn't this equal to 1 plus x squared plus, I forget what it is. It would make no sense to have units here, because then how do you add this thing that has no units to this thing that has units, and this thing has the units squared? That makes no sense. Okay, so the exponent, the T over RC, has to be dimensionless. But another way to look at this, that it has units of time, is resistance is volts per amp. And then we're going to multiply it by capacitance, which is a coulomb per volt, which is a coulomb per amp. But an amp is a coulomb per second. And here it gives you the units of seconds. So R times C has units of seconds. Okay? Units of time. So a lot of times we'll write the following. Well, we'll say this. Define tau is equal to R times C. And we say then Q equals Q max times 1 minus e to the minus t over tau. Tau is called a time constant for the circuit. Okay, tau is the time constant for the circuit. So the question you can say is, what is Q after one time constant? Meaning T equals tau, or T equals RC. That makes the exponent 1. And so e to the minus 1 is that. And so after one time constant, after amount of time equal to R times C, the capacitor is charged to 63% of its maximum value. Okay. So, I mean, you can write Q either this way or this way, it doesn't matter. You only use that equation if you're solving for Q given T, or you're trying to solve for T given Q. Otherwise, you have no use to use that equation. Okay? It is completely useless to use the equation unless you need to know Q at some value of T, or you need to know T given some value of Q. Otherwise, you probably don't need to use it. With students, they see capacitor problem, they just focus on this equation right away. Okay, and they might not need to do that. So just be careful. Okay. Do you have a question, Aaron? I'm sorry.
Is there any problems in homework related to this question?
I'm sorry, I really can't hear you. Can you type the question in the chat? It's just too hard to hear you, for whatever reason. Yeah, you'll see homework problems about this. There's about 3 or 4 homework problems where there's one long one where you hardly ever use this equation. You look at the extremes. You look at when t equals 0. You look at the steady state case. Steady state case means when this term is 0. When is this term 0? Well, when t equals infinity. Okay? So, and a lot of times in circuits, really all you need to do is look at the extreme cases. Oh, Matt, I'm not even on campus today. I'll be here on Friday. I'll be on campus Friday. I'm at home right now. Okay, I'm lecturing from home. Sorry, Matt. But I'll be here. I'll be on campus on Friday. Okay. So let me say a few more things. I'm not going to solve any problems today because we're kind of pretty much out of time. I just want to say a few more things. Since this is the equation for the charge on the capacitor and the voltage on the across the capacitor is Q over C, then if I divide this equation by C, then the voltage across the capacitor is delta V sub S times 1 minus e to the minus t over RC. How do I find the voltage across the resistor? Well, there's a couple of ways to do it. I use Kirchhoffs laws. The voltage across the resistor is the voltage across the power supply minus delta V sub C. And that'll give you So you take delta V sub S and subtract this from it, and that'll give you the voltage across the resistor. So another way to do it is that you know that the voltage across the resistor is I times R. What's I? Well, I is a derivative of this thing, or this. I is dq dt. And so when I take derivative, I'm going to do this one, take derivative with respect to time. I'm going to get C delta V sub S over RC times e to the minus t over, the negative signs cancel, just in case you're questioning that. If you multiply this by the resistance of the resistor, then you get this equation again. So delta V sub S over R is the maximum current. And notice that the maximum current occurs at t equals 0. The current decays exponentially as a function of time. And so after one time constant, I is at 37% of its maximum value because e to the minus 1 is 0.37. So here's a graph of the current, the charge as a function of time, showing you what its value is at one time constant. And the next graph I will show you is the current as a function of time. It starts at a maximum and goes to 0 as t goes to infinity. So again, I want to reiterate a term, and you'll see this in the homework, the term steady state. It's basically when the time-dependent part doesn't play a role, basically when t goes to infinity. Okay, steady state means that this term goes to 0. Okay, after you've waited a long time, the circuit stops changing. Because in reality, and if you look in the RC circuit, basically you close a switch and you have a transient, and the capacitor charges up. After a while, it stops charging because it reaches maximum value. And then everything's steady, although the circuit's boring then. So generally, when we look at RC circuits, or you do an experiment with RC circuits, you don't use a battery, but you use a power supply that does this. It turns on and off. So that you can see the capacitor charge and discharge. And so on Monday, when I'm on campus, I'm going to do a demonstration using a power supply that turns on and off. It's going to be essentially the same setup you're going to use in a lab later this semester. All right, I went over. Thanks for staying over. Any questions? Or concerns? All right, so I'll either see you on Thursday in office hours